Okay, so I'm gonna talk a few minutes about kind of the history of STM for those of you who weren't the Budapest meeting. And basically, what we're trying to do is there's three STM drivers now floating around. One from TI, one from STE, and now a new one from ARM. And what we're trying to do is figure out how we...
Three drivers for one hardware, not three hardwares.
Three different hardware, three different drivers,
okay.
Three different ways of talking to users.
So the hardware is different, but I thought it was a...
There's a concept of a system trace module.
So it's not defined by ARM.
The acronym STM.
Yeah, the only thing that's common between them is the protocol, which is defined by MIPI.
Oh, okay.
So MIPI defined a STP 1.0 protocol.
Okay.
TI went off and implemented a STM 1.0 module that implemented that protocol. And
okay.
STE went off and did something similar,
okay.
With different mappings and different control registers and a little bit different. I think STEs and TIs are actually more common or more similar than we are with ARM's SDP 2.0. MIPI recently, or about a year ago, maybe 2 years ago, came out with a new protocol extending the STM 1.0 protocol, and ARM built their module based on that SDP 2.0 module. So we'll talk a little bit about, there's a complexity with wanting to be interoperable with tools, validation plans. I actually have a plan, Michael, that you'll probably like, because it's completely platform-based, no host-based tools required. And we'll talk about how we get there, do that. And then we talk a little bit about what our roadmap is for OMAP, and then what we need to do to kind of move forward with these drivers, and then what do we do to upstream.
So this question I see, where does MIPI apply? Is that the wire protocol architecture? Is it the...
Yes.
Right.
Yes. It is actually the protocol out of the module, and then the data can either be exported off chip through pins, or in some cases, in all the TI cases, we can export the data internally to ETBs. ETB stands for Embedded Trace Buffer. So, so now I got to look at this first foil here real quick and see how much of it I've already talked about. So we talked about the MIPI SDP 1.0, 2.0 versions. Again, only the protocol standard, not the transport mapping or the control registers. You can actually have both versions of SDP show up in the same SoC. OMAP 5 actually implements both SDP a MIPI STM module and the ARM STM module. The reason is that we have a extra hardware message infrastructure in place at the SoC level that works very nicely with
Who is we?
TI. I'm sorry, Texas Instruments. Yeah, when I say we, I mean Texas Instruments.
Yep.
I've been with Texas Instruments for 30 years, and so I'm just used to saying we.
Yeah, you don't have it on your badge, so it's like
yeah, it should be. I should have my TI badge on.
Yeah.
So the difference between SDP 2.0 and 1.0 is 2.0 just supports a richer transport protocol. It has a improved common timestamp and just physically more channels. In SDP 1.0, you have a maximum of 256 channels. You can extend that with SDP 2.0 to 64K channels, and it's implementation dependent. I think the actual first ARM STM module that we're using in OMAP 5 only implements 256 channels. So again, STM provides just a simple protocol wrapper for common messages from across the SoC. It's both hardware messages and software messages. Software messages can be generated by any of the cores within the device, and hardware messages can then come from profiling modules that you can have many of in a device. We have some devices with 16 to 18 of these different hardware modules that are all generating STM messages.
Are those the same sources that we use for perf, for the...
No.
Okay.
No, these sources have not been integrated into perf, and I don't think the perf guys even know that this stuff exists.
So they don't have a software interface towards the operating system?
Exactly, exactly. Most of these modules can only export data via STM.
Mm-hmm. But they can be configured, turned on and off, and you could get the data back through the ETB.
Yes.
So they could be configured via perf, and you could loop them back into perf.
Yes. We have, basically, right now we have bare metal libraries that cover all the hardware modules for configuring. Some of the modules you can configure at very low levels through the APIs, but over the past year, we've kind of learned that most users are more interested in high-level use cases. And so recently, like with the statistics collectors on the OMAP 5, we've gone to a pure use-based interface for those libraries. So when you want to get something like throughput data on a bus, you just do the interface. You just tell it I want to do throughput with this master, rather than having to go through any of the details of understanding how to do that.
Is there a common way to configure those? Or does that depend on the individual source, how to enable?
Right now, it's just a library, so any application that integrates the library can enable it.
How does the application get to the hardware?
We just map the hardware back to user space.
So they've got
so it's in the case of STM, the software messages, you can have, generally you may have multiple users, software channels in a single device. And so in that case, you want a driver to be managing the channel distribution. Make sure you don't have any collisions.
How do you do that now? Do you have one shared device, or do you have multiple devices?
TI does that by allowing the user to create nodes where ARM, and I think that's the way STE does it. I think you just create a device node for a channel, right?
Okay, so
that's identical to the way.
It's a card out chart.
So we use, okay. TI, I'll get to that in a minute.
Okay.
TI and STE both implemented standard character drivers, where ARM has implemented a debug FS file system interface.
That looked a lot nicer.
So.
I should mention that the overall paradigm is that the idea with this thing is to get the bug data out to something on the outside that's running this multi-probe. Whereas I think we had a lot of talk about letting the system monitor itself, and that's possible with some of these hardwares, but and then it would use perf, of course, but
or
that's
F-trace.
or F-trace or whatever.
Right.
Yeah.
So, I tell you, let me keep going here, and I've got the next foil. We'll actually get into what the differences are between the drivers in a little more detail. So, the primary use case for STM is there's two primary use cases: the software instrumentation use case and the hardware message use case. So you have to keep in mind that there's both these use cases. In the software case. So what STM does is it assigns masters to every source of data. In the hardware case, those masters only transmit a single channel of data. In the software case, they can transmit up to 256 across 256 channels of data. The reason that MIPI STM implemented or defined the protocol that way was so that you can interleave messages and still, and without having to have any kind of protection on the writes to the hardware. So what the module does is when it senses that a different master or a different channel is being written to the STM module, it actually puts in the protocol another master marker or a channel marker indicating that the source of the data has changed. And so you can get away with no semaphore protection in the driver for the writes to the STM module.
I didn't get that. So why, if you've got two concurrent processes both writing into the memory mapped register, how do you make sure that?
Register.
Because yes, the transport layer is actually mapped across a fairly large space, and so depending on where you're writing determines what channel you're writing to and what kind of message you're writing, depending on whose transport you're using.
Okay. And how does it know that I'm done? Like, what happens if I just write a start message marker, then 1 byte, and then...
Yeah, that's an interesting problem. Generally in the drivers, in the TI driver and the ST driver, we just use the buffer that's being transmitted. We just packetize that buffer and put a timestamp at the end of it, and that's what we use to indicate the end of the message. ARM doesn't do that. ARM doesn't do any kind of packetization at all in their driver.
No, I still don't get it, but yeah, go on for now.
Okay, okay.
So you can keep on writing, you can have, say, 5 channels and randomly write to them, and you can decode those channels at the other end, but without a end of message marker, you can't
put them back
into
together.
your
Yeah, you have no idea how long an actual message is. If you're always writing characters, then you can always use the /0 at the end of each character buffer as the indicator. But we didn't. But we have no. But
did you say it ends up in one big buffer? So I don't understand.
Yeah, it ends up in one big buffer.
So I have 2 threads, each of them writing a message that starts with a message start indicator, and
Right.
then 1 byte here, 1 byte there, 1 byte here, 1 byte there. End of
Yes, each. Let me go to last
hardware
year's.
takes care of that. So say you had 4 channels. The hardware interleaves those 4 channels into one
Let
stream.
me show you what the.
And every time the
I have.
channel being written to the stream changes, you get a new master marker. So you could imagine your stream would be,
okay.
I'm channel 1, blah, 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 blah. Hey, I'm channel 4, I've taken over, blah, 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 blah. Hey, now I'm channel 3, blah,
Okay.
blah, blah.
Yeah. I
So
thought I
the
had
software doesn't write the start marker. It's
No,
just
hardware.
okay. Yep.
So you've
Yeah.
got 256 channels mapped to, say, 256 addresses.
Yep.
And depending on the address you write, it says, right, you've changed channel block.
Yep.
And so
Yeah, I thought I have a picture of that someplace,
Yeah.
but not in this foil set.
And
So it's only a stream, so as usual with a
Yes.
stream, if you want messages, you need an end of message.
Yep.
Yes, yes. It's a single stream, and as you change where you're writing in the transport layer, that determines when a channel marker gets added
Yep.
or a master marker gets added.
It's freeform, right?
We don't put any definition on what's actually within the data, other than the fact that the TI, we add a header to the data, and other than that, it's freeform. And what that header does for us, it's just a 32-bit, what we call it is an OST header, and what that header does is it defines the protocol of what's being written. So if we wanted to, generally most people think of character drivers in terms of just writing characters out. But since we have a bare metal library that uses the same decoders that we're using with Linux, that bare metal library can also transmit binary data, compressed strings, or character buffers, just like the driver does. So we use that little header to tell us how do we, what's the protocol, how to route the data to the right decoder.
so that's
and
the same method as the syslog protocol then, right?
the,
Syslog.
I'm not that familiar with that.
Syslog is what Unix uses for remembering events that happen in the system. Like, that's what everyone uses.
Okay.
There's a small header that says, well, this is a message coming from the kernel, it's long.
Oh, yeah. It's close to that.
Okay.
Yeah. So I would assume that syslog is the obvious use case for this. So you pipe everything from syslog into there and then have the remote syslog
Yes,
on the
yes.
STM.
Yes, we'd like to get to the point where we're able to do things like that.
Yeah.
Where we can take, and something I'll talk about when I get to the roadmap foil, that it'd be nice to be able to take kernel logging data and our hardware logging data and even user application data and correlate all that, in the same message set.
Well, that's what syslog does. I mean, there's a system call for syslog that says, well, here's a message, please put it into the global buffer, and then you can get it atomically out of the buffer.
Okay.
Yeah, but syslog either it keeps the message in the local buffer or it broadcasts. It sends over the network, so probably you could just send it to this thing instead. It would be a different target.
I mean, the syslog buffer should eventually map to one of the channels, and then you can nest it, because you have the channel header, and then you've got the syslog header, and then it fits in there.
Yes, absolutely.
Yeah, nice thing about syslog is its messages from kernel and user and everything, and a line as a record, and it's got a source and it's got a timestamp.
Now, with the STP protocol, it's not a wire protocol, it's the packet format protocol, correct?
Yes.
Okay.
Yes.
Now, the wire protocol can be anything. It can be like message registers with doorbells and that sort of thing, or because the remote device may also.
There's only 2 implementations right now of physical hardware protocol.
Okay.
There's right now STP v1, and at least in the TI world, uses a protocol called PTI, which is just you can define a clock and 1, 2, or 4 pins that you're broadcasting the data on.
Okay.
And it's very simple, just a clock for every data word, and centered and sampled, I think.
And on the other end of this, the device, whatever you're sending data to, it's not super intelligent, it's just...
It's generally some kind of capture emulator. We use, are you familiar with the TI's XDS emulators at all?
No. The reason I'm asking, I have a thought for Arnd of why could we encapsulate this on top of IP message?
Oh, on top of what?
IP message. Use the existing sort of infrastructure that OHA put together. I need to get a better understanding of the way
I don't think so.
work.
I don't think that matches at all, because that requires having software running on the other side.
Right. Okay.
Yeah, you can capture, right now we provide an emulator that you can capture the data with, the XDX 560 V2 system trace emulator. We're actually working on basically a larger model that will work for core trace also out the pins of the device. It's called the XDS Trace Pro. It will also collect STM data. And both of those, the STM data that we're collecting out the pins is generally running somewhere between 80 megahertz and 100 megahertz. The current capture box can run up to about 100 megahertz. Actually, the next generation, the Trace Pro, will be able to, gosh, I think we're going to collect, we're shooting for at least 250 megahertz, and actually 333 is the first instantiation of it. And then after that, I think we're trying to get to much higher rates.
What would be the use case for having such high bandwidth?
Well, you have to remember that the hardware-generated messages are generally periodic. So the more resolution that you want from the hardware messages, from things like bus throughput, power states, the deeper the message buffers you have to have, and the more data you have to collect.
Yep.
So you have hardware-generated message and software-generated message as well, right?
Yes, absolutely.
And what kind of messages the hardware can produce? Like you said, those power states and so on.
Generally, the hardware is generating messages, periodic messages that either indicate power states, clock states, or in the statistics collector case, it's a set of counters that get broadcast. and depending on how those counters are programmed, you can calculate things like bus throughput, link occupancy on the bus, or latency.
Okay, and then you want to correlate this with software-generated events.
Yes. And STM actually provides the natural correlation for all this, because in the end it's a single stream of data that's coming out.
Okay, but then
And they're all getting timestamped by the STM module.
And the hardware-generated messages, is there something that you can configure? You have to configure, or just it is fixed?
Yes, the hardware messages, there's configuration involved with those things. And we provide libraries to configure those.
Okay.
And the reason that we chose libraries is because normally it's a single application that's deciding how it wants to program those things.
Okay, and that part is highly machine-specific.
It's definitely module specific. The libraries are
module.
The control registers for the module are module specific, but the actual module.
What is the module?
The hardware modules. So
the bus controller, things like that.
Yeah. The statistics collectors have a large set of registers associated with them for programming different types of jobs. The PMI and CMI modules have quite a bit fewer registers associated with configuring jobs, but there's still a few for those.
So the configuration really belongs into the kernel. So what you have right now is essentially a user space device driver, which is normally not a good idea, because that means that you can't have a user space application that's independent of the.
You could implement it. You could implement it in the kernel too. The driver, these libraries are, like I said, they're bare metal libraries. The only thing that you need to in the libraries, what we do is actually export functions for malloking and mapping, freeing and unmapping. So all you have to do is export. All you have to do is provide us those functions, and we'll operate in any environment. So we're not tied to any one environment.
Okay, but would that make sense to put this in the kernel if it's highly, for example, if it's totally TI specific?
We have lots of drivers that are TI specific.
Okay, but the point of the driver is to expose like a generic interface to something, to some hardware. But in this case, if there's nothing generic to export, the only thing I see here to be generalized is for software to send messages.
Yes, and that's actually what we're talking about.
Otherwise, for configuring the hardware-generated messages, I don't see the point of having a driver for this, because...
No, we're not proposing a driver for that.
Okay.
Well, it depends on how similar these things are. Like, what are the kinds of settings you can do to different hardware sources? Like, is it usually enable, disable, change rate? If it's on that level, then I would say, then you should definitely have it in the kernel and expose a user space interface that says, well, here are these 100 sources, these are the names of these sources, and you can enable source number 23 and number 42.
So I would like to see, we might stop on this topic in a minute because it's a bit off, but I would like to see in the future a simple configuration interface that an end developer can use, probably exposed through the kernel. Think of it more like the PMU where you have, as you say, an on-off and a set rate, because I imagine that's going to be common across many.
Yeah, we went off and implemented a PMI and CMI device driver. Power and clock management device driver to just expose the setting up the control registers for those things, and we didn't really see any usage out of it, and so we're kind of thinking that we'll get a whole lot more usage out of a user level application that runs like a utility to set up these things kind of in the background.
If you have a utility, you typically want to have that shipped with a distribution. You don't want to ship source code to everyone who wants to use it. That's not going to scale. So, and when you want to have a common application to do these things, you need a common kernel interface. It does not depend on the specific hardware. You want to have the kernel internal part specific to the hardware, the device driver.
Right.
So then you've got 3 different implementations of the driver and one common implementation that doesn't know anything about the hardware, but can just probe what's there and enable and disable.
Yep.
We'll have to look at the complete use case.
Yep. I mean, I don't know how many settings there can be per source. If it's more than just a bunch of things that happen all the time, like enable, disable, separate.
Hundreds, I would imagine.
Yeah, it's more, in some cases, it can be quite complex. In fact, in the statistics collector, we don't even expose the interface registers for it because it's literally dozens and dozens of registers. Every little function that this thing does, they map to separate control registers. So,
right, but what would be an example of a function that is different from enable, disable, separate?
So it'd be more like I want to pick one of 30 different masters that are on the device, and I just want to see the throughput to the SD-RAM for this master.
Okay.
And so that's the level of the library interface, and we could do something very similar for a device driver if that made sense. But I guess where we come from,
we have a very similar. I'm not sure if you said anything about our stuff. But
no, I think we have it's conceptually 2 different things. That the STM and the link to the outside, that's some data sync that you can sort of configure. Then this is in both the TI and the ST Ericsson case closely related to some statistics collector that is probing around the system and providing utilization data about different hardware blocks and their masters and so on. But that, I think, is another issue.
Right. It's a totally different issue. It's just that they're both using the same data stream to generate data. So and because they generate the same data stream, we can correlate, in the TI case, we can correlate all those hardware messages back to, you'll see in time, the throughput messages correlated with application messages and kernel messages.
We had 2 approaches to that. We had the same thing. We wanted to correlate application events and kernel events with the actual trace data. So we have actually 2 outputs from our statistics collector. It's one interrupt-based, where we can collect the data inside the chip, and we have one where we can route it to this external just data port, we just gather it with a trace.
If we collect the data in kernel, we expose it through perf. So
actually no.
That's the idea.
It's trace events, basically.
Yeah,
So what we have is like a sysfs describes what we can enable disable. So it's like a tree of the masters, and you can enable if you want DDR bandwidth data or latency data. So you basically have sysfs describing because it's very hardware specific, right? So it doesn't matter, no point in making generic stuff. So we just expose the sysfs file. Sorry.
If it's sysfs, then it has to be generic in some way that you can describe it.
Yeah, I mean it's generic in the sense that it's a tree of stuff which you can enable disable. So, but you can't have an application that's it's a generic. We expose hardware specific stuff in a generic way.
Yes,
exactly. Sysfs is a tree of,
so that you can actually go into a specific folder and enable a specific statistics collection for this master. So the way you do that is generic, but what's available to enable is specific.
Of course.
But we don't need anything in user space, and then there's a special file for, like, if you want to send a message from user space and correlate that, you actually send that message to sysfs file, and it would just be part of the rest of the data, and you can trace that externally. But in the other way around, you can pipe the data back up in the system through interrupt. So you collect data. You can't do it as fast. You can't do it like nanoseconds or whatever, but you can do it like a couple of thousand times a second at least. And then you actually would just take the data and put it in a Linux trace event.
Right.
And there's also the trace events also have a file in user space where you can insert your data, and then you get the same timestamp. So there's really 2 ways of outputting it, locally in the system or outside the system. But you can both ways. You can correlate data because they from user space and the hardware because they all get the same data flow and same timestamp.
But the important thing with your interface is that the user space doesn't have to know about what the hardware looks like. It just has to look at what directives are there and it can
go in your folder and see what's available and then can play with that. Right. So whatever is available.
Right. So our first problem, we're kind of on to future problems rather than what we need to figure out right now. So what I'm going to skip to next is talking a little bit about where STM is. Right now, we've got STM on, maybe a dozen different devices, starting with OMAP 4. That's probably the one that most of you guys are most familiar with, but it's also present in a lot of other devices. That TCI 66, actually 14 and 12 devices are going to be devices that are, they're for communication infrastructures that are going to be running, they've got A8 modules on them, so they'll be running Linux, and they're combined with DSPs.
When are those coming?
A few months.
Okay.
I'm fairly sure they're publicly released. I think you can get the data sheet for at least the 14.
Right, I mean the source code. When do you expect to have that upstream?
What do you mean source code?
For the CPU, the SoC port.
Yes.
Oh, I have no idea.
So I think
we're discussing that here.
Yeah.
Yeah, I talked to one of the engineers working with that, and it might be on hold, waiting for some of the OMAP stuff to get cleaned up.
Okay.
So it's kind of a hybrid OMAP diversity processor.
Yeah. The 14 is definitely based on a lot of what went in OMAP 4. Now what we've done on OMAP 5 is there's both the STM 1.0 module for hardware profiling and ARM's STM 2.0 module. And so where we're at right now is we've got drivers. We have a driver for TI's STM 1.0 module, which is a character-based driver. And we have a driver for ARM's module, which is really more of a expose the hardware to user space type driver, and I'll get into more of the details of that in a minute. And then ST also has their driver for a maybe 1.0 module on their devices.
Yep.
What we did in our driver was actually, since we have this nice data sync, we also went into the trace functions and added hooks for, say, print K, trace, print K, trace function, and so on, so we could get that out on the multi-pro. So that was pretty useful. So I think we should use that.
So both TI and STE have got these 1.0 STM modules that are simple character drivers. They both implement message packetization based on timestamps, which our decoder requires. The TI character driver, and I think STE's also relies on the user assignment of channels to device nodes. So you just make a node and you assign the channel to the device, and then you know exactly what your device name is, and you can then redirect I/O to that device since we're doing the packetization, or you can make calls directly to the driver if you open the device, and you can make write calls to it.
So that means that you can transparently redirect standard output.
Yes.
To this.
Yes, absolutely.
Okay.
We do one extra thing with our driver that ST doesn't do is wrapping it with this OST header. Let's see, we already talked about that. I don't think it's just a 32-bit word that provides extra routing and decode information. And it allows us to differentiate between compressed messages, character buffers, and binary data.
So in terms of implementation, Steve Rosted said that Perf has some type of sync data from user space functionality in it at the moment, but it's a bit new. So you can't just have a device under /dev at the moment. But that may be how we implement it in the future. It may be the Perf is the answer, I think. But that's another side topic.
Yep. And then one thing STE driver does that TI doesn't do is it maps you can map a channel back to user space. And when we did our driver, we didn't really have a use case for that, but I think we actually do now. There are times we're thinking that we'd like to do functional profiling and correlate that with our hardware profiling data. And to do that, you need very, very low overhead writes to STM. And the only way we think we can get that is by not doing the the copy of from kernel user space to kernel space. We have to avoid that. So mapping the hardware, the transmit or the transport mechanism back to user space for that case is probably a reasonable use case.
How much
in that case, though, it's not generic anymore. It's specific to your hardware interface.
Yeah, as soon as you start using libraries, it starts becoming specific because.
Or I mean, even if you map it into your space, it means that you know the register layout.
Yes, the library has to know the register layout for the transport.
So it's not generic anymore.
No, it wouldn't be generic anymore.
Yeah, so let's not think about that even for now. I mean, that would be a future extension. Like,
But I
you
don't-
first have to think about whatever driver
Yes.
we move
Put the
into the kernel would.
Is it
things in
really a
place
performance
and then-
issue for data? I mean, how much data?
Absolutely, because what you're trying to do is get out generally a pointer to a function name, and that's it. That's all you want to export and a timestamp. So it's a single 32-bit write to the correct transport
I mean
register.
to trace like every function call in the...
Right. So you're not only, it's not just every entry point and every exit point from every function.
A lot of functions, but little data.
Yes.
So it's not. I thought,
Yes.
I
Yes.
thought it was a lot of data.
Yes.
There's no
No.
overhead.
Very little data.
Yeah. I understand.
So when you turn on gprof, when you do instrumented debugging, your performance drops to about 60% of what you had, and that's with running 20 or so instructions on every function.
That would be a huge overhead.
Right.
Yeah. So if you had a kernel user space switch as well, then...
Right. We'd like to get this down to 2 or 3 instructions.
Yeah, I know. Yeah, I understand.
So,
But, I mean, if you always, like if all the hardware can expose a single location where you can write to, then it will still work, right? Like if you have an
yes.
You don't
generic
have to
interface.
expose all the channels. You don't have to expose all the channels.
Right.
So if you have a short
Right. You only have to expose the one channel that.
Yeah, and but in order for that to work, the interface has to be the same on each of them. That in the sense that you can do a single 32-bit write to one LMIO register and actually ends up as a message. If that's not the case, then it doesn't work. Or it has to be something else that's the same over all of them. I don't know how they actually work.
But then you have the risk also because you can only protect like 4K or page, right? So you actually expose all the other registers at the same.
Yeah, you have that problem.
So you have to make sure that the hardware doesn't expose something that can crash or open up security holes. And stuff.
Yep. But in the case of STM, you're only exposing
at least
things
if you want to make that available to non-root users.
It could be routers, yeah.
You can always say that if you want the fastest interface, then you have to have permissions for that.
Yeah, because it's for debugging, it's not for...
Just hope that your STM IP block is not sharing a 4K page with other things.
Yeah.
That would be strange.
Like the bus management.
No, the transport mechanism take a lot of space in the chip, so I don't think that we'll have a problem with overlapping on the other functions.
Yeah.
So what we're trying to get out of this, we've got 3 drivers now for different implementations. TI would like to have one driver that works for both STM 1.0 and 2.0 at some point in time. That we will migrate upstream for OMAP 5. And but it's real important to us that we maintain backward compatibility with our existing drivers.
You can't. No way. There's no way you can provide backwards compatibility with the existing drivers.
If you want a generic driver, you're going to have to come up with...
Yeah.
You're going to have to look at all the drivers and look at all the tools out there and say, where's the kind of common functionality we want? Come up with a agreed upon set of user space interfaces and then code against that.
If you want it upstream and you want it backward compatibility, you need to keep both base. Otherwise, upstream cannot be the place where all the backward compatibility modules are. You will need to carry that on your own.
So the whole discussion that we're having can only be about how should someone write a driver for this. We have three examples to look at. We can take the best of all of them and do something else and make sure that it works for all the hardware that we have.
Yeah. The problem, it also has to work for the tool chain that you're exporting the data to.
Oh, sure.
And
we have a number of constraints, what we need.
Right, so
we need to make a driver that...
So I'm not familiar with SDE's tool chain, with what you guys are using. In our case, we have to have, our tool chain requires the OST headers on the data, and it requires the data to be packetized.
Well, that's fine, because that part you can abstract it behind your character device drivers.
Right.
It probably cannot be done for the memory mapped one, but let's put that aside for now. But the character device can packetize things into the format that you require.
Right.
At least the user interface would be generated the same for everyone.
Right. And that's kind of what we're thinking, is that maybe we just take ARM's driver, tack on a character driver implementation into it, and then make those things, what I'm kind of thinking is it'd be nice to be able to plug in either a TI module or a STE module into that.
Yes, of course. I mean, the way to implement a subsystem like this is to have one module that implements the user space interface as a base module that exports function calls to other kernel modules, and then have a hardware-specific module that uses those exported functions to register itself to the user space interface.
Well, I thought when you were talking about backward compatibility, is, for example, if you want to preserve your existing library, it might not work with the interface.
Yes.
You might come.
So you can
That's fine. We haven't implemented a library to work in the Linux environment yet, so that's fine. So the library we have today is just a bare metal library that understands how to talk to STM channels. So if what we did was just memory map the bare metal STM channels back to user space for those cases, our library would probably work fine.
So if the library isn't currently used by anyone and you don't distribute it yet, then you don't have a backwards compatibility problem.
Well, we distribute it. It's being used, but it's only being used in bare metal cases right now.
And we're talking about Linux,
right.
Okay, I thought you were saying that some user space binaries were built with that, and you wanted to preserve their ability to work. If that's not the problem,
no, that's not the case. That's not a problem yet.
Okay, then
it could get to be a problem fairly quick. We have people within TI, guys working on the graphics engines are looking at integrating STM for message logging into their stuff, and
well, we don't care about graphics people because they don't tend to work with us.
Well. This will be the first team that's looking at within TI that's looking at using both the libraries and the driver together.
If they're flexible enough to change the whatever interface we come up with, then it's not a problem.
Yeah.
I understand that on the consumer side, you might have those tools which are probably much more difficult to change, and anyway, we might not care as much.
Right. I don't think it's a problem yet.
The consumers, you mean on the outside of the system?
Yeah.
Yeah, that's like both TIs and our tracing department, they are sort of in the business of creating a big library that takes that data and creating a Eclipse interface or something similar where people can then get it in nice charts. That's like what it's for. And that's their core business. So this driver thing is just some necessary evil to get the data out of the system.
Right.
Yeah.
Right. Exactly.
Yeah, so that's like LTTNG or something like that.
Yeah, if we can abstract the packaging away from the interface, that's fine.
Yeah.
Yes.
That's great.
Yes, that's exactly what we want to do.
That means less trouble for everyone.
Is a standard character driver that hides the packetization is exactly what is what we have today, and is what, frankly, is what our users are expecting us to provide them.
And then if you want to mix in some hardware-generated events, probably the SSFS interface would be.
I think we should really make sure that we have some channels in the software interface predefined for specific uses of the system. Like we would certainly want to have one for syslog and one for the console.
Yeah.
Sure.
And there are probably a number of others that people can come up with. So we should have a common registry for these channel numbers.
Build it up as long as it comes along. Like,
well,
yes.
if we have, like,
we've actually.
If all the existing systems have a statistic collection for bandwidth per master,
Probably you
things
could
like that, maybe we
associate
should
those.
standardize on the names. And
You could use SysFS to match those.
No, I really not the. You can't match the early console because that has to be known at early boot time.
Well, I could use channel 0.
Yes, that's what I'm saying. We should pick one and document that so that nobody else uses the same one.
Okay.
Yes, it's already.
For print case.
That concept's actually been, well, I was expecting to see that in ARM's driver that they released, but the actual release didn't have any dedicated channels for anything.
Yep.
So when I was talking to the guys that actually developed the driver, we had talked about that concept.
It doesn't have any console driver.
Yeah, and it doesn't have any facility in it for anything other than broadcasting raw messages right now.
And that's, I mean, what I think we really want is a way that we can have the console output as early as possible, even before we get to the serial port. I mean, as I understand.
Yes, this should be something that works immediately out of the box.
Yes.
When you, in fact, when you get the first board, it'll work.
No, I mean early in terms of boot time. Like we load the kernel, we can.
Of course, we can just consider it as a special UART. It's not that a big deal.
Yes, and have. I mean, we have the common layer, and then we have the hardware-specific driver registering to that, and at that point we should get all the console output of all the print case that happened until that point.
Yep. Yep, absolutely.
And that should there should not be any specific headers on the console channel, so that you can always just read the data on every single vendor.
The only thing that we have to do from the driver, I believe, is just export some simple APIs to be able to do that.
Well, if you want to,
no,
the
driver does not. The driver cannot export any APIs. That's the common driver can, not the hardware specific one.
Right. The common one could export a set of kernel level APIs specifically used by kernel modules that want to register data with it, or the other way around. Yep. Would it be the other way around, that the driver would actually register or provide a registration function to these things, and it would automatically?
The hardware-specific driver registers to the common code that handles all the STMs. And the STM at that point can register a console driver.
No, what I'm talking about is the common STM driver to pick up the kernel logging data. Does it need to register with the kernel?
Yes.
Or does the kernel need to make calls into it?
No, it would register as a console driver. Yes.
Okay.
And we can have multiple of them anyway. So whenever the print case called, then the code will just call that console driver, which then massaged it into the STM format and so on.
Okay. So the way that you do it, at early boot time, we scan all the devices that are there.
Right.
And then we call into then we look if we have a device driver for that. And when we find the STM device driver, because we know that there's the STM hardware there, we call its initialization function.
Right.
That initialization function from the hardware-specific code calls into the generic STM driver, and the generic STM driver calls into the console driver and says, I'm a console.
Okay.
Unfortunately, we're about to get kicked out. There's another session after this.
Yep.
Well, we haven't even got to what's different between ARM and us.
Well, no, I mean, the kernel hacking room, so I do want to share.
Yeah, maybe we can do that.
Yeah. Okay.
I think the general idea is that we need to come up with some generic infrastructure for this.
Okay. We need to write down the requirements for a new driver for this, like for the common driver.
Right.
and then find someone who implements that.
So
Yeah.
that's the interesting one from my
It's probably me.
Yep.
So we do have a 15-minute break here, so we're not getting kicked out right now. So.
We should wrap up, right?
Mm-hmm. Yeah, we don't have any action items, I think.
Because
Yet. We should have.
these things seem to be much more simpler than I expected at first time.
Yep.
Yeah, this is actually kind of back to when I was here, when I was at the Budapest, when I made a proposal for a kind of an STM framework that vendor-specific drivers would plug into, and we're back to the same solution.
Yes, it's still needed.
Yeah, yeah. Yeah, what we're hoping we could do is take ARM's solution and just massage it enough to make it work for us, but I'm not sure that's
It's a prototype.
Yeah. Yeah.
There's interesting things in this.
It's not a generic layer, and it's not interacting with any other part of the kernel directly.
Yeah. Well, the big problem with the ARM driver is you actually have to understand the SDP protocol to use it. They actually expose the complete.
Why is that a problem?
Well, do you want
that should have to be separate into the machine-specific module.
Yeah. Do you really want to have to understand SDP protocol to be able to use it?
No, you should not.
Well, use it
The
from
driver
what?
has to understand, or the
No, the user of the driver has to understand. In the ARM case,
But the user of the
we
driver,
should-
if the user is a console driver, then that can very well understand the protocol.
Yeah.
Because it's always the same protocol. It doesn't. The protocol. Then the protocol is always the same.
No.
The protocol should not be part of the hardware
No.
specification.
This transport layer maps many registers. Yeah, each register represents a different type of protocol it's tacking on. So if you want timestamps with your messages, you have to write to one register set. If you want just bytes out, you have to write to one location. If you want just 32-bit words out, you have to write to another location. If you want the data guaranteed, you have to write to one location in the ARM case. If you want it to be lossy, you write to different locations.
So basically, it's not possible to have the common fast path to be exposed one register. Because in our case, it's not just one register, because it's multiple registers, and you need to select the right one depending on what you want.
If you're trying to form complex messages, you'd have to understand the protocol to use ARM's driver. Whereas in the TI case and the SD case, it's a character driver, you just write to it, and we take care of all that complexity for you.
In their driver, from user space, you need to be aware of all those details.
Yes.
Okay, that's wrong.
Yes.
That's wrong.
Yes.
So even if you just want to sync standard out, you still have to understand it.
Yeah, you'd have to know what you're writing to.
That has to be
use it.
abstracted through your machine-specific driver.
Now, they provide a default location that writes 32-bit messages with a timestamp on every single message. So if you're writing hello world would get broken up into 32-bit words, and every 32-bit word would get timestamped.
Yeah.
Whereas in our case, hello world gets one timestamp at the end of it. And that's the right, we feel that's the right way to do it.
Sure.
Yeah.
Right, so what's the next step then? Talking a bit more about what the implementation could be?
Yes. Well, I think we also need to talk a little bit more about the differences. I think I need to finish up this because there's some initialization stuff that ARM does totally different than what we do with debug.fs that I think we need to talk through and make sure that...
Initialization should be hardware dependent.
In the SDP case, are we going to get kicked out of here in a second? Or?
Quarter past.
Next
section.
Okay. In the SD case and the TI case, the user has to make a node. And in our case, I don't think in the STE case this is true, but in the TI case, when you make a node, you're actually doing a physical channel assignment. And I have arguments with people within TI as to how valuable that is. But one value of it is if you're making the physical assignment yourself, when you look at your data, you know exactly what channel your data is coming in on. You know exactly what your device name was, and you know exactly what device you're using. In the debugfs case, you have to, echo out to a debug subsystem file system. You have to send a code to a debugfs file that's already been created to create a channel. And in that case, at least in the current implementation, all they do is take STM channel underscore and physical channel number, tack it on, and that's what they call the file that you write to. Well, the problem with that is that you don't know which channel. The channel assignments are dynamic. You have no idea which channel was assigned to you. So in the case of when you have many channels open, how do you know which one is open for you?
You want logical channels, right?
Yeah, you
channel
need some,
that actually represents something. And
yeah,
then some start
right,
package
that name.
that actually identifies it.
Yeah, if we were going to stick with this convention, I think we've got to do something different.
So is it okay to continue this in the kernel hacking room, or would you like to schedule another session? The thing is, Doug's not here for very long. You're here.
I'm here all day tomorrow and Thursday morning.
I really need to get something else done. I wanted to send out patches yesterday. I had